morning, good afternoon, everybody. I want to start the seminar today. It is my pleasure to introduce Professor Jerzy Kijowski. I think everybody knows Professor Kijowski here, so I don't need to say much. He's one of the mentors of our institute, and he's a great specialist in theory of gravity. And today's lecture title is Variational Principles. There was some subtitle, I remember, but let's not share the details now. So welcome.
So can you turn on the lights? So this talk is going to be an undergraduate talk. I'm going to share with you some observations related with the use of variational principles, which very often leads to a nonsense. And I propose some issues, how to avoid those nonsenses. This talk will mainly be in mathematics, but very simple mathematics. However, all I have discovered during my very long life in this domain is related with physics, and in fact, the outcome is, I believe, very important to physics. Okay, so the subtitle is on dangers and ambushes awaiting a theoretical physicist as soon as he starts to apply them. I will begin with a short history of variational principles. So the first one was proposed by Snellius, a great Dutch physicist, engineer, and mathematician. And the story starts with the following simple exercise in mathematics. Namely, the horseman must ride from point A to B. Partially, the travel will be over grass, partially on sand. Velocity over grass is higher. And which way should one use in order to get as quickly as possible to the goal? So naive horseman will probably choose the straight line, but the intelligent horseman will observe that it pays to lengthen a little bit the fast part of the travel if it shortens the slow part. And actually, this is a very simple exercise in differential calculus, because the total time is t1 plus t2, which is the distance divided by velocity. So after all, we have to minimize the function of a single real variable, namely the crossing point. And already on the first year of the differential calculus, the students showed that the result is the following, that the minimal value is obtained if and only if this Snell law is fulfilled. And now the genial intuition of Snellius was that probably the refraction of light is also due to the same phenomenon. Of course, he had no chance at that time to measure the velocity of light, but he had this correct intuition that if you replace grass by air, sand by water, and if again the velocities, the relation of velocity is like that, then the shortest way corresponds to the refraction law, which is now called Snell law. The next step was the Fermat law for light rays in an inhomogeneous material. And he discovered that, but this is just a simple generalization of the Snell law, namely, if the velocity does not change in an uncontinuous way as in previous example, but is just a continuous function of the position, then to calculate the trajectory of a light ray, we may approximate this continuous material by collection of narrow slices where the velocity is constant. And now, at every transition point, we know that the Snell law must be fulfilled. The total time is just the sum of all those times which at each transition point we have actually to minimize the function of a single variable. Therefore, we obtain a good approximation, which is not a smooth curve by a polygon like line. And now, if the approximation gets better and better, which means that those fringes are made more narrow and more narrow, then we pass really instead this time, instead of being given as a sum, finite sum, it becomes the integral, which means that this trajectory assumes its minimal value. Now, of the distance divided by velocity, now the distance is given by the physical metric. Therefore, we may introduce something which is the optical geometry. And now we may say that the light rays are geodesics with respect to this optical geometry. But the very birthday of calculus of variations in physics was the brachistochrone problem. This problem was invented as a challenge by Johann Bernoulli, who invented this problem and sent it as a challenge to the best contemporary mathematicians. And it seems that all of them were able to solve this problem. However, Newton was probably the fastest one. Okay, so the problem consists to find a curve on which a massive point without initial speed must slide without friction in a uniform gravitational field in such a way that the travel time is minimal among all the curves joining two fixed points. So this is, roughly speaking, this problem. And the solution is always a balance between the two tendencies. The shortest one, this is the shortest one, and the fastest one, because this trajectory makes the ball to in the fastest way. However, the winner is this curve, which is called brachistochrone, which realizes this balance between the two tendencies. What we are using as physicists is due to Maupertuis, and later its generalization by Hamilton. Maupertuis was motivated, Maupertuis was great. He was able to measure the Earth 15 centuries after when Greeks were able to do that, and it was not very great. What Eratosthenes, 200 years before Christ, were able to do was a very good approximation. In any case, he was a very clever man, but he was highly motivated by Leibniz philosophy, that we are living in a best, our world is the best possible. This philosophy was so much ridiculed by Voltaire. Everybody of you who read Candide by Voltaire sees that the entire book is devoted to ridiculization of this philosophy. In any case, Maupertuis was very much impressed by Leibniz philosophy, and he was able to show that some laws of mechanics really come from this, he called it least action principle. So nowadays we are very often using this approach that there is some function which nowadays we call Lagrangian or Lagrangian density function, which depend upon position and velocity, and we try to minimize this quantity. Okay. So this is, if you open any textbook in the calculus of variation, this problem is called single integral problem, but of course we may, it was quickly generalized to multiple integrals. As an example, take elastic two-dimensional material whose configuration is described by one dependent variable and two independent variables. And the total energy is the sum of gravitational and elastic energy. Gravitational energy is proportional to the haze. So in order to minimize gravitational energy, the sheets should lie on the Earth. Whereas elastic energy is proportional to the surface, which means that to minimize it, it should be flat. And optimal configuration is a balance between the two tendencies. This leads to very nice mathematics, and which I am going to skip here. And finally, due to generations of mathematicians and physicists, we have the present formulation of calculus of variations, which lead to Euler-Lagrange equations. So let me introduce the notation here. So there is, suppose that there is some space of independent variables. In physics, very often, this space is just our space-time, but I don't need to assume that. So very often, for instance, in general relativity, there are 4 independent variables. There are some dependent variables, and there is some Lagrangian density, which depends upon values of those fields. Those dependent variables, you may call them physical fields, which live on space of independent variables, and their derivative. I am going to use this notation. Whenever I add some index downstairs, it means that I am considering partial derivative, partial not covariant. I don't assume that there is any covariant derivatives. By the way, when I was young, was student and then a young assistant, I was taught that the partial derivatives are used by non-education peasants living in villages, whereas we educated people, we use covariant derivatives. And why? Because the partial derivatives are not geometric objects. And this is not true. Partial derivatives form geometric objects, which is called in modern geometry jets. This terminology was introduced by great Belgian mathematician Eresman. Okay, in any case, I'm going to use partial derivatives, and the formulae which I'm going to use are coordinate invariant, which means that there is a specific law how to translate them from one coordinate system to the other. So nothing, no conclusion depends upon the choice of coordinates. In calculus of variations, one uses very often one parameter family of field configurations. I'm going to denote by epsilon this additional one parameter, and the delta, which is very often used variation, is simply the derivative with respect to this additional parameter. Just a simple remark that in order to obtain this coordinate invariance, which I have mentioned, this Lagrangian must be a scalar density, because in many problems, very often the space of independent variables is already equipped with a certain measure. Therefore, we may divide the scalar density into the standard measure and a scalar function, but this is rather exception. But in general relativity, this is not the case, but because, okay, so the Lagrangian is not a scalar, but a scalar density. Okay, and the calculus of variations begins with this formula. There is nothing especially exciting. If I want to differentiate the value of this Lagrangian density with respect to epsilon, so epsilon is here and there. Therefore, I must integrate over field strength and its derivative. However, then we change this formula into an equivalent formula by integration by parts. Namely, this derivative, we first put it on the complete on this object, so this is that, and I must subtract the derivative of that. So this formula is totally equivalent to the upper side, and this is then identity. It does not carry anything, any information. It is just an identity, and the calculus of variation begins when, by the way, this part is called volume part, boundary part, because if we integrate, then this gives us the volume integral, whereas this gives the boundary integral. However, the real equation begins if we kill one of those terms. And the standard way to kill it is to impose boundary condition. Namely, we say we are looking for the minimum, but only among those fields which fulfill some boundary condition at the boundary. Because if all those phi's which we are considering assume the same value, then the derivative with respect to this additional parameter epsilon vanishes. And this way, this term is killed. And what remains is simply to minimize that, which simply, if this derivative is equal to 0 for any variation of phi, this means that this coefficient multiplies. These are Euler-Lagrange equations, and we are studying this the first year of physics and mathematics. And this is an excellent strategy whenever we are doing the true variational calculus, which means that we want to minimize something, or in other words, whenever these equations are elliptic. So in logistics, economy, traffic engineering, and so on. However, in dynamical theories, like in field theory, this approach leads to a nonsense, and this is what I am going to show you. So I will understand
Not know yet whether it's a minimum, really. The stationary.
it is never minimum, but it is not the main problem. Everybody knows that it is not minimum, but the problem lies much deeper. I am going to discuss. So as an example, let us consider the two-dimensional wave equation, which is mother of all dynamical theories. Whenever somebody tries to formulate some statement, some theorem about any kind of waves, for instance, gravitational waves, I advise to check whether this statement is true in this case, because every also gravitational electrodynamical waves are described by wave equations. Okay, so this simple example, I consider two-dimensional space-time. The independent variables I will call time and position. And as a Lagrangian, I take standard thing, which is just the difference between the square of the time derivative and the space derivative. I will always denote by dot the time derivative and by prime the space derivative. So Euler-Lagrange equations is very easy to write down. This operator is called wave operator or D'Alembert operator. But it is very easy to solve this equation. Namely, we pass to new variables, which are often used light variables. And it is very easy to express both time and space derivatives in terms of the derivative with respect to u and v. And if we plug this into the definition of D'Alembert operator, we obtain simply the second mixed derivative. And now consider any rectangle in this light variables, which means that I consider space-time region where U runs from the value A to the value B, and V runs from the value C to the value D. And now, take any solution of this wave equation because and integrate it. Because it is a solution, then this must vanish, so it is 0. But on the other hand, it is very easy to integrate derivatives. So if after the first integration I get that, but after second integration, I simply obtain the combination of the values at the corner point. So I have shown you that wave equation implies such an identity for every region of that time, but it is very easy to show that it is equivalent. If function phi is such that for any rectangle in light variables, this identity is fulfilled, then this function fulfills wave equation. It is very simple. Okay, so now consider just the standard region of space-time. And we know that for any such a rectangle, this identity is fulfilled, which simply means that the value, boundary value on the upper wall is uniquely given by the combination of the values on the left wall, right wall, and this, the remaining. Which simply means that if we try to choose boundary conditions at random, then the probability that we are able to capture any solution is exactly 0.
Yes.
Which means that this strategy, which was used to derive wave equations from the variational principle, is based on a nonsense. Yeah, we are able to derive field equations under conditions that we already know. But it doesn't mean that whether the Lagrange equations are not true. However, we should somehow avoid this nonsense. Now, if I use another, because this region was very specific, if I use a region with the rectangle having commensurable dimensions, then again the problem becomes a little bit more complex, but still manageable because we may add those identities corresponding to each square in such a way that the values that inside this region cancel, and finally again we obtain some identity for the boundary. However,
those waves are actually standing waves, right? Or wrong?
simply you are unable to choose freely boundary conditions.
Of course.
Yeah. And that's all. It's a very simple observation. However, if you, yeah,
At the beginning, in the original variable, can you choose boundary condition A? at the very beginning, X and T. Can you choose any boundary condition?
But in which region?
You want some region and you choose boundary condition.
I'm just starting to discuss.
Because I also, I have experience that when I change variable in this way, I have problem, but the problem is really, it's the problem of changing variable.
But the very
It is not.
meaning of differential geometry. I have written a book in differential geometry where I have given a definition what is differential geometry. Differential geometry is an art to use mathematical analysis in such a way that the result does not depend upon the choice of coordinates. This is, according to me, the definition of differential geometry. Okay, in any case, if you use a generic shaped region, the story is very, very difficult. If you want, when I was young, I spent, I believe, 1 or 2 years trying to give answer for the following question. Among all possible, if I take the space of all boundary conditions, how to characterize those which admit any solution of wave equation. And the answer is that it's very difficult. This is not a regular subspace in any reasonable definition, because you have to define what kind of, how smooth are those, and so on and so on. And it is really a very badly defined problem. So better do not try to because the boundary value problem is not.
That's right. So perhaps it's better to say that such a simple wave equation should not be considered to be derived from the variational.
No. I am going to. The main goal is to show you that if we change the philosophy, okay. So this philosophy, I call it brachistochrone strategy because it behaves, because it is based on an approach which was used by Bernoulli, Newton, and all those people, and it is correct. And in that case, why? Because the boundary value problem is well posed, whereas for hyperbolic field equation, it is not well posed. Okay. Nevertheless, so we already know that it is not correct. Nevertheless, for instance, in Wheeler-Missner-Thorn book, which I still consider the best introduction to general relativity, even if it was written 50 years ago, I believe. It is still a good book. However, in a part which is devoted to variational principle, on a page number 520 something, they calculate this variation of the Hilbert-Lagrangian in general relativity. They calculate the volume part, and they said, no, we are not even trying to calculate the boundary part because it is useless. It doesn't, because in any case we are going to kill it. Okay. However, I claim space-time boundary conditions are strictly forbidden. Okay, so instead of this brachistochrome strategy, I propose it is possible to use another strategy, namely, whenever you give me a Lagrangian, I say, I am interested only in on-shell configurations, which simply means don't when this part vanishes, which simply means that without neglecting one of those terms, this is just an identity which does not carry any information. When we kill one of them, it becomes an equation. So this is my equation. And I claim that it leads, first of all, to a very nice approach, mathematics, and we do not lose anything. It is useful to introduce the auxiliary variable, namely the derivative of the Lagrangian with respect to the derivative of K, we may call momenta, and this way, this equation, fundamental equation, which really contains the entire information about field equation, is maybe written that way. So, or in that way, yeah, because if the partial derivative acts on that, I obtain this quantity. So my equations may be understood in the following: that the derivative of the Lagrangian with respect to derivative of the fields are those momenta, which means that we recover the definition of this momenta, and the derivative of the Lagrangian with respect to the fields are equal to this. And we immediately notice that if I plug this equation into that, I immediately recover Euler-Lagrange equations. So what is the difference? Euler-Lagrange equations are second-order equations for field configurations, is now replaced by first-order equation, but for two different objects, configurations and momentum. Before I describe the mathematics which arises in a natural way here, I may say the following. You may say, but who cares about which way do you derive field equations? What really counts are equations, and these are the same equations. But in general relativity, and I will probably come to and say 2 words about general relativity, it is very important which objects do we take into account. So, this approach to the calculus of variations fits into the symplectic control theory, which is very often used by engineers. If there is only one independent variable, namely time, so we have the standard Lagrangian formula, which you may find in Landau-Lifshitz book. However, the man who first noticed that this formula, this is a trivial formula, tells you that the momentum is a derivative of Lagrangian with respect to velocity, whereas the p dot is equal to the derivative of the Lagrangian with respect to the position. This is trivial, nothing new. However, the man who first noticed that this formula should be interpreted as a symplectic control theory was, by the way, this equation means nothing but the following, that there is a four-dimensional, not two-dimensional, but four-dimensional big space described by positions, velocities, momenta, and forces. And within this four-dimensional space, there is a privileged physically admissible states form a two-dimensional submanifold, which is described by this equation. The first who noticed that this very old equation may be interpreted in a symplectic way was one of my teachers at the Department of Physics, Warsaw University. And I would like to show you that this kind of mathematics was already there. Physicists knew it already in 19th century. Namely, the first law of thermodynamics of a single body is written the same way. There is a four-dimensional space. Volume, pressure, temperature, and entropy. And for a specific, and this is a meta theory, but the theory of a specific thermodynamics material, for instance, one mole of a specific gas, is given if we know this function. This function can depend upon two variables, and the physical laws governing this system are described by these two equations, which are simply the same like here. And now let me, when engineers use this control theory, they very often use the following terminology, that this is control-response relations, that there is a big four-dimensional or many-dimensional space. In this space, we have some quantities which we call control parameters, and the remaining which we call response parameters, and the physics consists in measuring relations between them. Okay, now let me summarize a little, because I'm not going to go very deeply into the mathematics, but let me summarize the main mathematical structure of these spaces, of those. So, the symplectic control theory is the following theory, that there is a big space, this four-dimensional, which is equipped by a canonical symplectic structure. This symplectic structure is given by the very notion of this object, by the form which is a word, roughly speaking. So in the field theory, this space is consistent of field strengths, its derivatives, momenta, and the divergence of this momentum. In mechanics, this big space is described by these four parameters, in thermodynamics by this form. And now, this is not yet a physical theory, but metaphysical, because it is a theory of any mechanical system. Now, a specific system is described by a submanifold which contains all physically admits points, and geometrically this submanifold is what the geometers call a Lagrangian submanifold, which means that it is isotropic and maximal, which means that the symplectic form vanishes when applied to pairs of vectors which are tangent to t. And now, dividing coordinates in P, in this big symplectic space into two groups, control and response parameters, the D may be described by a generating formula. This is the generating formula in field theory. This is in mechanics. This is in thermodynamics. So roughly speaking, situation is like that. However, the D may lie may be situated in this way, which means that it is a graph of a mapping, which means that to each value of control parameters, for instance here, there is one and only one value of response parameters and so on. However, it may also happen that this D lies in this way, which means that we have constraints, namely, some values of control parameters are excluded. For instance, if you choose this parameter, there is no physical point which corresponds to that. Moreover, control-response relation is multivalued. So from this point of view, of course, the difference between this situation and this situation is terrible, is very. However, from the point of view of the big space and the subspace, there is no substantial difference. Yeah? Why? Because the role of control and response parameters may be changed. This depends upon the way how do we measure the things. So very often we have such a situation. So from this choice of control parameters, here we have the theory without constraints, but here no. But if we slightly change this reference system, we immediately see that regularity is not a property of dynamics, but of the control mode. And control mode is our choice. How do we describe our physical system? And in fact, the swap between control and response is understood as a Legendre transformation. For Legendre, let me show how do we perform the Legendre transformation. The simplest case of thermodynamics, we rewrite this term as d plus b, and then we put this total derivative on the left-hand side, and we obtain a different control mode. And this generating function is now called enthalpy. Yeah? And now we instead of controlling entropy and volume, we control entropy and pressure. In the transition between Lagrangian and Hamiltonian formulation is exactly the same. We simply rewrite this Lagrangian formulae in a full analogy with what we do in thermodynamics. Next, we put the total derivative on the right-hand side, and we call the new generating function, the not energy, but the total minus energy. Now, and so the whereas Lagrangian mechanics consist in controlling positions and velocity, whereas Hamiltonian dynamics is just the same, everything is the same. However, our choice of control parameters is now different. Now we control positions and momentum. And in field theory, one could think that we may do the same. However, because there are many independent variables, so maybe we should exchange the role of all velocities. In space-times, we have 4 of them with all momentum. And this is what mathematicians do in the true calculus of variations, where they are trying to really minimize some. So for mathematicians, the energy, but it is not a physical energy. I have very quarrel with my friends, mathematicians, which say that we have to exchange the role between all velocities and all momenta, but it is not the case. What we feel it is called an energy for us, because energy is not a scalar or scalar. It is a part of energy momentum. Therefore, what we call energy is based on the choice of a reference frame, which means that we, among all those typically space-time parameters, we choose one of them which we call time, and the other ones which we call positions. And now we, among 4 momenta, we choose one of them, which I'm going to use by a specific letter. And now we do not choose the space part of that. We only exchange the time derivative of the field with this time component of the momentum. And this is how do we define field energy in physics. I'm slowly coming to the end of the story, because you may say, okay, it is not very much exciting, because how do you look on equations? It's not very important. What is important are equations. Okay, but I was trying to understand the modern theory of gravity, and I was reading a lot of Einstein's papers. During 4 or 5 years, he tried to invent the description of gravity which would be consistent with his relativity theory, which we nowadays call special relativity theory. And his considerations was based on the notion of inertial frame. He tried to understand what is inertial frame. And at a certain moment, his friend, Marcel Grossman, told him that there is a nice lecture about Riemannian geometry. So he learned Riemannian geometry, and he abandoned this track. However, if you try to use that gravity theory the way I have told you, maybe it is worthwhile to come back and to see that the previous attempts by Einstein were not so stupid, were extremely important, and they lead immediately to a very broad extending of the present general relativity, which I will shortly mention here, and maybe in some future I will offer a talk about that. Okay, in any case, the geometric structure of space-time is described by two a priori independent objects, namely the metric and the connection, which in my opinion, and I believe this was one of the most important things I have ever understood, is nothing but precisely what Einstein was looking for, namely the field of inertial frame. And the correct formulation of Einstein theory is due to David Hilbert. Einstein visited Hilbert, spent 1 week in Göttingen, and the Hilbert's assistants were laughing our Putzfrau knows geometry much better than your Einstein, which was almost true, because at the time Einstein was studying geometry and he only was beginning to understand it. In any case, there in Hilbert's configuration, metric is called configuration, while gamma is taken as momentum. However, and this is this formula which Wheeler, Wissner, Thorne give on page number, as far as I remember, 520 something, and they are not even trying to calculate the boundary part, but many years ago, I believe already in the 70s, I have for myself calculated this boundary part. It is very, very easy, namely this pi with 4 indices is uniquely given by pi with 2 indices, and this pi with 2 indices was first used by Vladimir Alexandrovich Fogg in his book written in 1938, I believe. So my modest approach consists in slightly changing the coordinate, not the coefficients, because so I noticed that the Fogg description is much better than the standard description of variational principle. So I'm not going to use this Brachis-Tochron formalism, but the Hilbert, but the on-shell approach. And if I do that, then immediately you see that the metric, we find it on a level, on a side of momenta, whereas gamma enters as configurations. And this gives rise to the what I have called affine approach. General relativity may be completely recovered. However, this approach gives to, first of all, from the very beginning, there is room for cosmological constant here, and there is a room for unification of gravity with electromagnetism, and also there is a room for something else, and I very much hope that this something else will correspond to what we are looking for as dark matter and energy, and I will probably stop.
That's a good question. Please,
I question because you actually described two ways to derive equation of motion. First one is you just throw away the boundary term and you got actually equation of motion. And next time you use on-shell condition to focus on the boundary term, and you got also same equation of motion.
Of course,
But
yes.
how come actually you always get the same equation of motion?
Pardon me?
How we can get always get same
How
equation?
come you get the same equation?
Because
The equations are the same. However, the way you are putting them together is totally different. Yeah? For instance, in general relativity, I claim that gamma is not an auxiliary quantity, but it is a priori a different quantity. In standard general relativity, you from the very beginning assume that gamma is a Levy-Civita connection defined by the metric. But I also know how to get this equation, but it is not just an ad hoc assumption, but we may get it if we choose the Lagrangian in a specific way.
Regarding the question, is it related to adding some gauge term to the Lagrangian? Like if you add some derivatives of something, can you show that equation of motion will still remain invariant?
Yes, I will show, but not today, because today I will stop here.
Yeah.
I meant this talk as a talk for children, but next time I will.
And the second question regarding the discussion regarding the boundary condition. So if you have a two-dimensional wave equation, one can ask the question, are you allowed to have arbitrary boundary conditions? So what's the...
No, you are not allowed. I don't know. You are not allowed to have the free boundary condition, to choose free boundary condition in a hyperbolic. Between zero. That's all.
So my question was like just specific to this wave equation, because it's like a mathematical question. But
Yeah.
you can have, for the wave equation, can you have arbitrary boundary conditions? If not, how do you check that the boundary condition that you are imposing is consistent with that, which tells you cannot choose freely?
I don't understand the question. You just check whether you first, you impose what you are allowed to suppose, and not, you are not allowed to suppose boundary conditions. You are allowed to suppose initial conditions and space boundary conditions, but not space-time boundary conditions. You solve, and then you get some boundary conditions, and you see what. But the space-time boundary condition cannot be supposed.
The question is, what kind of boundary conditions or initial conditions are you allowed to use in specific situations?
Yeah, like
That's
whether
a very subtle, subtle question.
Yeah, because your solution depends on your boundary condition. So that means arbitrary
Well,
boundary
what does
conditions.
it mean? It depends on boundary conditions if you are not allowed to choose first before solving you choose boundary conditions. You are not allowed to, because if you choose them, then the probability that you get any solution corresponding to those boundary conditions which you have chosen is zero.
Yeah. So it's very often boundary conditions on the spatial boundary. In that case.
No, I was talking about space-time boundary condition. Okay, You may, in hyperbolic theory, you may assume freely. As I have shown, there are 4 walls. You may freely choose the conditions on 3 walls, but not on all the 4 walls. Therefore, you are not allowed to specify space-time boundary conditions in hyperbolic theory.
We have questions from Zoom?
No.
No. Any other?
I have only comment. I experienced situation in statistical physics. So you integrate in some variables, and you, for instance, the channel, right? There is size in the perpendicular direction and in this the wrong direction. And you choose coordinates, the standard coordinate of your disks. And then integration is simple, right? Because the integration rate domain in this direction is just plus minus, that's it. But then you want to improve integration and you change variable exactly this way. You introduce distance between the disk, not the coordinate, but distance. And then the problem is that then the integration domain is no longer like constant. It depends. You know, it's from x1 minus something to x2. You cannot integrate it. And if you want to change it to some constant, then it's wrong. It's already a mistake. Or at least it's approximation. At the beginning, what you showed, maybe it has connection because I experienced, you know, I had really bad problems with this. Exactly, I just change variable from x, y, z, x minus y, z minus y, and so on. And the problem was that the domain changed very much and very
No, I was talking about changing the domain has a priori nothing to do with choosing.
Question from myself.
Last question.
In what sense are now boundary conditions or initial conditions different from the, let's say, space-time ones in these wave equations? How can you sense the difference in the formulas? Because you can specify what boundary conditions in the light form or no problem.
Very interesting. I know how it is.
Yes, but I understand that there must be some kind of fundamental difference between these 2 cases.
Yeah, that's also no, my claim, which I gave you, is that for a standard domain, it is very, very difficult to describe the space of the boundary condition, which is compatible with the solution.
What might be easier, it sounds like you have formed some kind of.
For example, like it was very easy just for a square, which I have told now. Of course, I have illustrated my talk by something which was similar. Of course, very easy.
Let's thank Professor.